And then these nodes would need to re-execute transactions again. So re-execute.
So everyone's duplicating basically the same work.
Yeah. And they basically do the same work. So like this leads to actually several problems.
All right. Hi, everyone. I'm Shane, a research partner at Hack VC. And I'm joined today by Bobbin, who's at Miden. Do you want to introduce yourself, Bobbin, and what you do over at Miden?
Yeah. Hi, Shane. Excited to be here. Yeah. So I'm Bobbin. I'm one of the co-founders of Miden. I've actually been working in Miden for almost 3 years now. First as part of Polygon, and we recently spun out. I think there was an announcement like about 2 months ago. Now we're an independent entity, kind of building basically the same thing I was building at Polygon, but now we're getting much closer to launching into the market, and so we're operating as a separate entity. I am basically the original author of the Miden protocol. So like I came up with it 3 years ago and have been working on it ever since. And now, it's grown into a good company. We're 20 plus people right now. And so, hoping to go to mainnet, either later this year or maybe Q1 next year.
So there's basically a testnet out.
Yes,
Okay.
there's a public testnet. It is an alpha testnet, so we will transition to like a beta testnet by the end of the summer. But for now, like you can actually do a lot of things. We have a few very interesting builders already building on it. Still rough around the edges, but we're improving with every release.
Yeah, awesome. Yeah, so do you want to give like the basic background behind like why Miden needs to exist and what it does and at a basic high level?
Definitely. I think like the way I think about Miden, the way we think about it is that it is like a next generation of blockchains. We call those edge blockchains. And maybe before I get into like what Miden is and like why we call it an edge blockchain, it may make sense to kind of explain what's the issue with the current blockchain. So like how does it fit in?
Yeah,
And
sure.
so
That sounds great.
Yeah. Also, basically, in my mind, has been so far two major kind of like inflection points in the blockchain tech. The first one we just got blockchains. No. And the first one was Bitcoin, and there was obviously many more, but this was like the first generation of blockchains, and they lacked quite a few things. One of them was programmability, right? And so the next evolution was programmable blockchains. And the best example, the most known example, is Ethereum, obviously, but there are many others. So I think of edge blockchains and Miden as the next inflection point in this chain, and what we call is like the next evolution would be edge blockchains. And the fundamental difference between previous generation and the edge generation is like where does the computation happen and who stores the data. And to give like a little bit kind of overview of how traditional chains operate, like the first two generations, what we usually have is like, let's say there's a node or a block producer. So this would be a block producer. And, you would have users. And the users, there could be many of them, would be sending transactions to the block producer, right? TX1, TX2, and so on and so forth. And the block producer would need to execute these transactions, right? So they collect the transactions from the users and then execute transactions, put them in the blocks, and then they send these blocks, executed blocks, to other nodes, right? So there would be like many other nodes on the network. So this would be nodes. And this goes through P2P networking and all that stuff. And then these nodes would need to re-execute transactions again. So re-execute.
So everyone's duplicating basically the same work.
Yeah. And they basically do the same work. So like this leads to actually several problems. Problem number one, as you said, it's just like duplicating word. I call this execution bloat.
And storage.
Exactly. Because we need to re-execute all transactions, we actually need to have the entire state available to us. Otherwise, we can't execute transaction, and that leads to state bloat. And the third thing that is maybe not obvious, but immediately, but it basically, because we need to store the state and because we need to re-execute all the transactions, we can't have privacy, right? Everybody needs to understand what they're executing or have access to all the underlying data. And so the issue here would be no privacy. Because again, for me to execute something, I need to know the underlying data that goes into the execution of transaction, and I need to be able to run all the computations. So I need to know the program, and I need to know like the balances and everything else. And so we get into the situation where we have these three limitations. Like everybody needs to execute everything multiple times, as many times as there are nodes. We need to store all the data, and then we also don't get any privacy because, again, we have to have access to all the data. And this is like the fundamental limitation of traditional blockchains. I mean, in fact, you couldn't do a blockchain in a different way, right? Because the core property of blockchains up until recently has been that they verify by re-execution. There was no other way to verify that the state is correct for you to get the
And this is true for basically every blockchain, every L2, like pretty much any one that you could name has these three issues.
So basically, yeah, for every, and this was basically up until I would say relatively recently was the only way to make the blockchains work, right? You couldn't get around this. Bitcoin couldn't get around this. Ethereum couldn't get around this. Solana can't get around this because we didn't have the tools. Now, we now do have the tools to change this model. One of those tools is, or the main tool is ZK proofs. What ZK proofs allow us to do is to run the computation, verify it, or prove it, and then send the proof to somebody. And so somebody else doesn't need to re-execute those computations. And so we can shift to a different model. So like this is the edge blockchain model, where you have users still. What they do is they execute their own transaction, and then they prove the transaction. And these guys do the same. And then they send proofs to the block producer. This would be proofs. And this would be the block producer. And so the job of the block producer then becomes much simpler. You need to aggregate the proofs. You don't need to re-execute anything. And you need to, like, depending on the model, you may just need to like recursively aggregate them into a single block, and that would be the ideal thing. And then, what you do is you send one big proof. So you get the transaction proofs. So this would be like TX proof. And here you could send, to the rest of the network, and this could be like multiple nodes, whatever. You just send one block proof. And what this means, the rest of the network just needs to verify this single block proof. They don't need to re-execute it. So you can even imagine a node being run on a smartphone, for example, and it has enough computational ability to verify basically a limitless amount of computation. I mean, there are some limits, but it's practically limitless. For practical standpoint, it doesn't really matter. And this is one of the core properties of ZK proofs, by the way, that verifying is exponentially faster than executing the computations themselves. Now, being able to do it in this model where you have, and again, maybe I should draw a nicer picture. You have users that execute and then network. This is users. Just verifies. This addresses very nicely the problems that I described before, right? So like, first of all, there is no re-execution. Second, you can be in a situation where the state is actually stored on the user side. So state could be here. I don't need to share my state with the entire network. What I need to share is just the commitment. So what goes, commitment is a fancy word for hash. So you just hash the state and just send the hash. And so you basically end up in a situation where your state could be, your wallet could have like a ton of different storage under it, a lot of assets and all that stuff, and the only the only impact that has on the main chain is like 32 bytes, regardless of underlying complexity of your storage. And it's a bit more complex than that, but like roughly, you don't need to scale as much the network storage, and so. This is the second benefit. And the third benefit, naturally, because if you run your own computations and if you store your own data, the network doesn't need to know about this. And so you get privacy by default. So this is the third benefit. Now you have options of how you want to do it. Like there are different ways. You can still share things and disclose as you wish. But you get this benefit where, unless you do something extra, you remain private. And I actually think this is the right model, because if you think about privacy, and one of the reasons I think it hasn't taken off yet, and we can discuss like things around privacy, is that if you have to like give up a lot in terms of UX, or a lot in terms of like costs to achieve privacy, a lot of people will not do it. Like I remember using Tornado Cash at some point when it, a long time ago when it was legal, and I think it's legal now again. But at that point, and like running a transaction for Tornado Cash was categorically more complicated than just doing a regular transaction, and it was also like probably 100x more expensive than doing a regular transaction. So like in this case, like you really need to think, do I need privacy or not? In this model, it is the opposite. You need to pay more to be public, because if you think about it, you need to ask the network to store your state or the network to run your computations, and they incur more kind of like cost for that, and so they need to be compensated. So if you remain private, it actually would be cheaper for you to do so, and so I think that actually aligns incentives quite nicely.
So flips the switch. So do you want to get into kind of like ZK proofs, maybe the basics, and kind of how they pertain specifically to Miden?
Yeah, for sure. So, I mean, ZK proves the basics is that, what we want to do is we have some computation, right? Let me do it this way. Yeah, let me start over here. Sorry. And this could be some function like f of x, whatever. We have this computation has some inputs and produces some outputs. What we can do with ZK, like usually, like if I want to run a computation in the context of blockchains, that would be like proving it, executing a transaction, right? So like I have some inputs, I apply it to my account changes because of that.
Like the current state, basically, blockchain state. Yeah.
Yep, exactly.
And the transaction you want to add on to it.
Yeah, and so I get like a output, the new state of the chain and all that stuff. So if I want to verify that you've run this computation correctly, for example, usually, like as we discussed before, I would kind of have to re-execute the same transaction. ZK lifts that because what ZK says is that, and I'm not going to go into like how ZK actually works, but what it allows us to do is say, okay, I'm going to run something else, like I'm going to run the computation and I'm going to run this mathematical proof. By the way, let me know if you would want me to get into the nitty-gritty details of ZK. I can do that as well. You run the computation and you get a proof. And so somebody else, so like this would be the prover. And then let's say there is a verifier that can just get the proof, and they still need to get the inputs, and in this case, like the outputs as well. And they would say, okay, yeah, this computation checks out because I verified the proof, and with this inputs you will get with this proof, this inputs you would get this outputs. I don't need to rerun the computation. This is one of the nice benefits of ZK proofs. The other nice benefit is, which is like in traditional computation, it's not even like kind of possible, is that we can have two types of inputs into a computation. We can have public input, public inputs.
Because in this specific case, if you have the inputs and outputs, there's no privacy, basically.
There's no
'Cause it has
privacy,
the full
exactly. Yeah.
blockchain state. Okay.
Yep. You just save on computations, like, yeah. So like you don't get the privacy, you can get full inputs and you get full outputs, and you just verify that you can get one from the other without rerunning the computation. But now we can also have the second thing is private inputs. And so when the user verifies, they only the verifier, when they verify the proof, they don't need to have the private inputs. They only need to have the public inputs into the computation. So you can hide data in ways where the verifier doesn't need to be exposed to some data. And a good example of this is that, for example, I want to verify a bunch of signatures, right? And I want to say like this proof attests to the correctness of like 1,000 signatures that I verified. I don't actually have to send the signatures to the verifier. I just need to say, okay, I had this, the public inputs would be the public key and a message that was signed. And then inside the computation, I prove that, yes, I had the signature that was provided as a private input that confirms that this message was signed by this public key. And so you can basically think of this as a data compression in a way, because, right, you had like 1K signatures, each one of them was 32 bytes. And then you can generate a single proof that attests to correctness of 1,000 signatures, or maybe even 1,000,000 signatures. And this proof doesn't really change too much in size. Basically it changes. It's either completely fixed in some proving systems, like it's constant, or it grows logarithmically, which means like you increase the input like a millionfold, and then maybe the proof size like increases 50%.
Yeah. Are there private outputs as well? Is that another notion?
Not, I mean, you can think of it like technically there is like really no outputs, like everything is an input, like even the outputs can be treated as an input. So you can think of your output could be a commitment to something, and the actual like data that could be private. So like you don't need to reveal the full output. So for example, in the case of blockchain, if you have the blockchain state, the new state, you don't actually need to reveal the input in the full state. You can just reveal the commitment, the root of the state, and say this is enough. I know what this would result from, and the actual state could be private, but the root has to be public. So you can think about this this way as well. But yeah, so I think this is kind of ZK proofs. I think another important thing, by the way, that has recently happened that we're using in Miden and now many teams use as well is ZK VM. So you have ZK proofs, right? ZK proofs have been viable for some time. I think like the first version of Zcash launched was like, I think the first like practical implementation of ZK proofs. They were very circuit specific for a specific thing. They used like trusted setup and all that stuff. But they were like first, as far as I know, like real in production use of ZK proofs that people could do. And I think, we can double check my memory on this, but I think it's like 2017 or maybe 2018 timeframe when they launched this. This proofs required you to do a lot of things, like you had to handcraft the circuits for this computation. So like they were circuit-based proofs. And so people who would be able to create those proofs were very few in number, right? Like most developers would not be able to write like a circuit that would be something that you would run a ZK proof against. And in fact, like one of my like when I first got into like ZK proofs, I should have given a bit of background about myself in the beginning, but I got into ZK proofs like around 2018, 2019 timeframe. And my first inclination was like, okay, this is like so difficult. Nobody's going to use it if it is so difficult to use. How can we simplify it? And so like my first attempt was to do like a ZK DSL that simplifies writing the circuits. But then I figured out that that's kind of going to be like a steep learning curve anyways. And then one of the next things I tried was a ZK VM. So I think one of the evolutions here is that we have ZK VMs now. And ZK VM is a really nice concept. Conceptually, it's very similar to the previous one. So if you think, this is your ZK VM, you still have your kind of inputs and you have outputs. And this, like, I'll just, for brevity, just keep it inputs. You have private inputs, public inputs. But one of the things that you can also provide as an input is the program. So you don't need to encode, you don't need to come up with a circuit. You can just feed the program itself is an input into ZKVM. So ZKVM is a circuit that somebody built for you, and then you can just provide the program, and you still get like the proof as an output here. So by the virtue of executing some program on this ZKVM against some input and getting some output, you get the proof. And this is really nice because then most people don't need to worry about circuits. I mean, people who design and build ZKVM need to worry about circuits, but vast majority of people do not. And we have now different types of ZKVMs, right? You have ZKVMs that have custom DSLs for them. Like I think a good example of that would be Cairo that Starkware uses, right? So and it's like, let's say Cairo. You have other types of ZKVMs that, you have RISC-0, for example, right? Or you have succinct. I don't know how to spell succinct. But you have RISC-0 and others that are able to do like, this would be like a RISC-5 VM, right? And this is nice because now it's like a custom language. You get ability to use Rust as a programming language to write. So you basically write Rust as a Rust program. I mean, there's like a little bit of a learning curve of like specific interfaces that needs to be used, but in practicality, that's just Rust, and then you can execute on ZKVM. You get a proof, like you almost don't even need to know that there is a ZK stuff happening underneath. With Miden, we have kind of a hybrid approach, by the way. So we have a custom ISA. But we have a compiler from Rust, so you can still use Rust as your programming language, but it gets compiled into like a custom, not RISC-V VM, but a custom virtual machine code, and then gets executed on my VM. And I can go into like pluses and minuses of different approaches, but now like the biggest takeaway is that developers don't really need to know anything about ZK that is running underneath. Like for Miden, you just write Rust programs, and every time you like execute a transaction, it generates a proof automatically for you because the VM itself handles all of that mechanics underneath.
Wait, so is Miden EVM?
No, it's a custom
Okay.
VM. So I mean, there are ZK EVMs as well nowadays, quite a few of them. Which like if we go back to my there's custom ISA and custom language. We have like standardized ISA like RISC-V, and then you can use Rust, and then you have like another category here would be like ZK EVM, which is basically EVM bytecode, and then you write its solidity usually. So
so like if you're a smart contract developer gonna make a smart contract on Miden, let's say, you're basically gonna write a Rust program,
correct,
which will get compiled by your compiler.
We still, so like actually like to get a little bit more technical, the way it works in Miden is that we have we use standard Rust compiler that gets compiled to WebAssembly, and then we compile WebAssembly to Miden assembly, and that gets executed on the VM. So like technically, like anything you can compile to WebAssembly, and there are some restrictions, but you can run and execute on Miden. So Rust is just the main language that we're targeting, but you could, for example, do C or maybe on C++ and other languages that can target WebAssembly. So the compilation pipeline is slightly different. It gives a little bit more flexibility, but also like for the future. But for now, again, just for from this focus standpoint, it makes sense just to focus on Rust as the primary smart contract development language.
Yeah, and I guess zooming out a little bit, what does the state look like?
On Miden,
On
you mean,
Miden,
when you say
yeah.
state? I think that's a very interesting thing. I'll get into it in a second because it actually works very differently. But it's a good question. And one of the things I want to mention, so like well, if we go back to the very beginning when I said like, okay, so there are traditional chains that had been operating in this way, and they couldn't operate in a different way because there was no ZK. So like ZK is one of the ingredients that you need to make edge blockchains possible. But just ZK is not enough. You wouldn't be able to apply ZK to, let's say, Ethereum or Solana and get an edge blockchain out of it. What you also need is a different state design. And the reason why you need a different state design is because most of the blockchains, because they didn't have to kind of worry about somebody else like running proofs separately and then sending proofs to the chain, because the assumption was baked in that the chain executes everything. The way the state was designed was like not easily segregatable. And what I mean by this is that, for example, if you and I both want to send USDC at the same time to somebody, both you and I need to touch USDC smart contract. And that means we cannot independently generate proofs of our transactions against USDC smart contract, because if I do it and you do it, the state of the contract will be different and only one of our transactions will go through. So you get into the state contention problem, and that's like the reason. And so you need to design the state in a very different way for you and I to be able to execute transactions independently and then send them to the chain, and the network can then like still make sense of them so that there is no conflict, or at least like minimizes the conflict. And so the way Miden does it, and I'll start with how like actually transactions work on Miden, we can go into the state design after that. So the way transaction works on Miden, if I wanted to set assets to you, for example, so like let's say this is my account, and we have a concept of accounts on Miden, and it's very similar. Accounts are very similar.
Basically a public key, public-private key pair.
They're very similar in design to like Ethereum smart contracts. So like every account on Miden is a smart contract. So what is frequently called account abstraction. So like you can actually you could do it with a single public key. You can have a multi-sig in it. You can have like very complex logic in it, and smart wallets, what sometimes is called. But every account like is a smart contract on Miden. But in this, they're very similar to Ethereum. I'll get into some of the differences, but you can think about it for now as an Ethereum-like smart contract. Now, there's a new concept in Miden, which is called nodes. And this comes from what we call like an actor model. It's a very well-known kind of model in kind of distributed and concurrent systems, where you have like actors that maintain their own state, and they communicate with each other by exchanging messages. So in Miden, there's a concept called nodes. And accounts can create nodes and can consume nodes. Conceptually, you can think about nodes as UTXO. Bitcoin has UTXO, and there are a few other blockchains. So like Miden is actually a hybrid of like account state model from Ethereum or Ethereum-like chains, and then UTXO-based chains. So you have both accounts and you have UTXOs, and the accounts can create UTXOs and accounts can consume UTXOs. So like when I want to run a transaction, I can create a node out of my account. So let's say I had like 10 USDC in my account. I create a transaction, so this would be a TX1, where I move some of this 10 USDC. So let's say I keep 5 and put 5 into this node. And then, so now I have like situation on the blockchain. This is a transaction that can get recorded where there's like one node with 5 USDC and my account with 5 USDC. And then let's say you have another account, and then you would consume this node. And as you consume this node, this 5 USDC would move into your I should know how to spell. Would move into your second account or into your account like on chain. So basically, we separate this. This would be TX2.
So that'd be two separate transactions.
Those would be exactly two separate transactions. I do the first transaction where I reduce the balance in my account and create a node, and then you do a separate transaction when you consume a node, kind of destroy it. When you consume it, you destroy the node, and you increase the balance of your account. Now, the reason why this happens this way is that it naturally separates the state transition of my account from your account. Like I don't need to know anything about your account to be able to update my state, and you don't need to know anything about my account to be able to update your state when you receive the note. This would be a problem in Ethereum, for example, if I wanted to, like, the analogy that I frequently make is that in Ethereum and many other blockchains, I'm just using Ethereum as an example, like for me to be able to send something to you, I kind of like have to take your wallet and put the money into your wallet. And while I'm putting the money into your wallet, nobody else can touch your wallet because your state can be updated one transaction at a time. And but at the time when I put the money into your wallet, it is locked for everyone else. In this model, I kind of take the money, I put them in a lockbox, I give you the key to this lockbox, and then you can open the lockbox later and get the money. And so I never actually hold the lock on your wallet, so to say. And then, kind of describing the transaction model in a bit more formal way. So if this is a transaction on Miden, so there's it always updates one account. So let's say there's account and account one. So this is the state of the account, but it can consume 0 to n nodes, and it can produce 0 to n nodes.
So could a DEX work on this? Like, how would that work?
So I can describe that. That's an excellent question.
Probably a good example, maybe, to see how that would work.
But let me kind of like wrap up with this one, but and then we can go to a DEX example, because this is exactly like quite like how do we make the public share state work, because this works very nice when your state is
works well for
private.
Transfers. Yeah.
Yep. Exactly. Now, in this model, as I mentioned, like every transaction updates a state of only of one account. It can read states of many accounts. So you can, for example, read an oracle in the same transaction or do something else, but you can only update state of a single account, but you can consume and produce many nodes. So if I go back to the previous example here, right, you would say, okay, like now I have to do 2 transactions to transfer assets from one account to another. Maybe it's less efficient, but in reality, like these nodes can be consumed and produced asynchronously. So what that means is that I could wait until I have like 20 nodes and then consume all 20 nodes in a single transaction. And you can actually send in a single transaction, like make transfer to 20 different people if you want to. There's actually interesting potential optimization opportunities here where I may wait until like the gas fees are low to consume the kind of a bunch of nodes in a single transaction. I mean, obviously a human would not do it. It would be optimized at the like a wallet level or something like that, where you could say, okay, during the day, I don't consume all the nodes unless I really need to. I will just consume them at the end of the day when like it's most optimal for me to do it. Or you could do it every hour or whatever. Like it could be up to the software to decide how to do it. So in reality, there is no like you can amortize this and not end up in a situation where a single transaction or a single transfer requires 2 transactions. And in fact, you can do multiple transfers in a single transaction if you send out many nodes and consume many nodes. Now, to go to your DEX example, and actually before we get there, like to explain how we manage like different accounts and nodes on Miden. So we have 2 modes right now, both for accounts and nodes. So like an account could be either public or private. Public is basically like all the data on chain. You have everything about the account, its storage, the asset it owns, and everything else is stored on chain. In some ways, it's basically very similar to a typical account on Ethereum or Solana or anywhere else. Private accounts have only hashes of their state on chain, and the actual data, as I mentioned, lives off chain. And this is like where we get the benefit of compressing things. So like you can have public accounts and they would be more expensive because the chain needs to carry the state and apply transactions to them and all that stuff. And you can have private accounts that you only put a small commitment on chain and you are in charge of maintaining the data. And same goes with nodes. We have public nodes and private nodes. And we don't have this right now. In the future, we'll introduce also encrypted nodes. Encrypted nodes would be kind of, you can still store them on chain, but you can, encrypt them so that the data is not publicly visible. But now, imagine now we have the situation where we have private accounts and public accounts, and we have private nodes and public nodes. And so let's talk about like a DEX. Like we want to have like some kind of like an, AMM. AMM would be a public account.
It's got 2 assets, let's say.
Yeah, it could have like a number of assets in there, like it could have like a liquidity pool, whatever. It could have a bunch of things. And let's say there's account 1 and account 2. This could be private accounts. They and let's say they want to trade, like right with this through this AMM. I want to exchange USDC for ETH, for example, or something like that, right? So I would send a note, and this note would be so like note, and it would carry USDC. So let's say it has like USDC. And one of the things I didn't mention when I was talking about nodes is that on Miden, nodes have, besides carrying assets, they have this, like what I refer to as keys, but it's actually programs that you can execute. It's like a script that you need to execute to consume a node. And the scripts can be arbitrarily complex. Like in some ways, you can think about nodes as like on-chain intents, where you would say like anybody, whoever can execute the script can take the node, and I can target a node to a single account. I can target it to many accounts. I can target it to no specific account at all. And whoever can fulfill the condition would be able to consume the node. So in this case, for example, if I have this node that wants to interact with the AMM that I have publicly on chain, like I could detain USDC in there, but my script would say, okay, these are the slippage conditions that I'm willing to tolerate. This is like the returning asset that I want to get, like I want to get ETH in return, and like a bunch of other parameters I'm sure that you can come up with. And then you would send this node. And a different person would send something else. Maybe they want to trade some completely different assets. So there's another node that this, let's say node 2. This was node 1 that wants to trade some other asset. Maybe they want to exchange I don't know, like ETH for Miden tokens in the future, and all of that stuff. So what would happen is that the network, the block producer in this case, would observe there are nodes targeted toward this account, because this is a public account that can be updated by anyone. The block producer would say, okay, I'm going to create a transaction that consumes both of these nodes. So like I'm going to execute a transaction, and this transaction, I'm going to consume these nodes, apply them to the account, and as a result of me executing these transactions, new nodes would be created. So this node would carry whatever, like ETH back.
Ordering there is kind of set by the block producer.
The ordering is set by the block producer. So like the block producer would have to sequence the nodes. But there are actually interesting things you can do. For example, you could ensure that within this transaction, everybody gets the fair price or the same price. So like it doesn't matter how you order the nodes in there, because you could like the logic of the AMM contract can specify that unless everybody got the same price, like the transaction will fail. And so the block producer would have to I'm going to get into a bit of detail. He could like pre-compute the outcomes non-deterministically and then provide the actual information of how like this would need to play out when actually executing the transaction. And then you would get in a situation where you can't do sandwiching within this transaction. You could still do sandwiching across transactions, but within this transaction, you would not be able to sandwich nodes in different ways. But yeah, at least in our current implementation, and maybe we can come up with a way to do it differently in the future, the ordering of nodes is fully decided by whoever creates the transaction. In this case, it would be the block producer that creates the transaction, and they can figure out how to do it.
And so can a note trade on 2 different AMMs at once? That seems to start to get complicated.
It would be complicated. I think the main complexity there would be that you'll create a race condition where somebody will need to decide which AMM to apply it to, and if some like how to decide would get tricky. Right now, in the current implementation, we actually limit when you send a node to like what this is called like a network account, actually, like an account that's managed by the network in our nomenclature. You have to specify a single account. You can't send a node to multiple network accounts at the same time. Maybe it's a condition we can relax in the future, but for simplicity, like this is what we've done right now. But this allows you to do a few interesting things. For example, you could be a private account that interacts with a public AMM, and this node, like where it goes to, could be also fully private. This node needs to be public because AMM needs to know, like the network needs to know how to consume it. But even that, you can hide like the origin of this node. There are ways to you can do it. So you kind of get an anonymous AMM out of the box almost, where you know that trades are happening, but you don't know which accounts are participating in this trading. So like the fact that this account too did actually send this node and then receive the node back would be completely hidden, or could be completely hidden if you wanted to. This also means that like I can do some interesting things. Like if I can like in this node, I don't have to say that I want to receive the nodes back. I could send this node to someone else. So in fact, like I could say, let's say there's account 3. And then so like when the node gets created, it could be routed back to some different account. So I can exchange it, send to a different account in the same kind of like swap transaction, so to say, or in the same swap flow. And one of the interesting things, this could actually even go over a bridge, for example, right? So like you could, in theory, have like somebody swap something and send it anonymously across a bridge to some other chain. Like it could be sent back to Ethereum, or if we have a bridge to Solana, it could be sent to Solana. Where Miden is going to be integrated with Aglayer, and through Aglayer you could route it to like many other chains that are connected to that to the Aglayer. And so you could imagine this swapping and bridging and in an anonymous way as like a very interesting use case.
Okay, so some amount of composability is broken though, or like made a bit more difficult, right?
I think I don't know if like it's for sure a different model. Like I would say like the actor-based model is very different from like how you write smart contracts in Solidity. That is like definitely the case. I don't know if there's like a lot of things that are like inherent limitations that you can't do. Like there's probably a different way to do it, but you can do it. And there are things that you cannot do in Solidity that you could do here. I'm sure there are probably some things that are very easy to do in like EVM chain that would be more difficult to do in Miden. And there are some things that are very difficult to do in EVM chain that would be like trivial to do in Miden. Like as an example, you could have like, this is how to do an AMM, but we have a few pioneers, or actually, not maybe a few, but at least a couple that are working on a exchange where there is no account involved, there is no AMM involved. Like what you do is just match nodes. People create nodes, and if you have two nodes that are floating and then can be matched against each other in some way, you can resolve them without actually needing them to have liquidity pools. And that is an interesting thing. Like one of the other cool things that you can do in Miden with this node model is that, if I have like my usual picture here, account 1, account 2, and I create this node, because I can put arbitrary script in here, I can have the node be recallable. So like I can say like, this account 2 can consume this node at any point in time, but if they haven't consumed it for a month, then I can take it back. So I can get it back. And in this case, like this creates like in a sort of recallable transfers that if you screw up the address or something like that, or you actually don't lose the funds, you can take the node back if it hasn't been consumed in a month or whatever.
Or if in the DEX case, like the trade doesn't go through, let's say.
Exactly.
Yeah.
Yep. So you can encode these conditions.
Can you even do a case like, I'll take it back if the price goes down by at most, 0.2% or something?
It could be arbitrary, right? Like
Okay.
it could be like it could even depend on some external oracle, right? Like the node becomes like recallable if something else happens, and you can, or because in a transaction you can examine the full state of the chain. So you could say there's an oracle that, I don't know, that's an election outcome or something like that, right? And you would say, if this oracle like flips one way, one person can get a node. If it flips another way, the other person can get a node. And so there are different models like you can create with this or different ways to think about like common things that we do in one way. But like I do think again, it's different model, but like I don't know if there is things that you can't really express in them
Mm.
in this model.
And the idea here is that you can basically, like one of my very, very initial questions, which I think is now answered, is all these people simultaneously constructing transactions that are all going to be executed basically at the same time and they each have their kind of own views of the state. That normally doesn't work in EVM because the state is going to change in between the time that you submit and it's actually posted on chain. But with this, are you basically guaranteed that the note construction will always be valid?
I think, yeah, so you're always guaranteed that you can update your account correctly. Like I think the node consumption is a different story, right? Because like if the node can be consumed by two different people at different, like this node, as I said, like if let's say a month passes, then whoever consumes it first will get it and the second transaction will fail. But creating a node will always succeed. Like you can always send something out. Now whether there will be a conflict when you try to consume it depends on real, like exactly what you've crafted. Some nodes can be consumed by only one party and there will never be a conflict. And some nodes, like maybe you would create a conflict by the virtue of like it being able to being consumable by multiple parties, and and there are different ways to address it too.
And so
But
the
yeah,
note construction is a proof, and the block producer that aggregates all the notes, do they also have to do a proof that's different than the aggregated proof?
yeah, so like every transaction requires a proof, right? So whether it is constructed locally or by the block producer, all of them require proof. So in the end, like it basically the same program that executes is just like different people or different entities that execute it, right? So when a node gets created in this context, like I would run the proof locally on my device and create it. But in this like context, like somebody on the network, block producer most likely will need to create it. Although in the distributed setting, you can actually say maybe there are some other entities that go and create like searchers that go and create these transactions, and maybe they get a fee paid for that. And then the job of the block producer is just really aggregating the transaction. They don't need to pull any individual transaction themselves.
Because
Um,
like that aggregated kind of meta transaction, or even just the consumption of the note by the AMM, has to have its own separate proof
Correct.
because it has to
Correct.
know the state of the AMM. Okay.
Yep. Yep. But you can imagine this AMM could be like I said, it's a public account, but you can imagine a situation where it is run by some set of entities. Like it could be a centralized entity, or it could be like a consortium of sorts. They don't need to put the state on chain. They could have a state off chain. The people still send nodes to them. They run the computations off chain, so it's not even the block producer that does it. They just post the proofs to the chain, so it completely offloads the chain. So you can have kind of like, I mean, it's basically like a mini rollup itself kind of thing, right? Where this AMM becomes a rollup effectively. And one of the ways that I sometimes describe Miden is like it's basically taking the rollup concept of Ethereum and like pushing it to the limit where every account in theory could be a rollup. Uh, uh, you basically get the, I mean, either rollup or a validium. If you store your data on chain, you are a rollup. If you store your data off chain, kind of like as I described here with private accounts, you would be a validium. Um,
Yeah. So then what is the relation to Polygon? So how's that
of
going to
Miden,
work? Yeah, or is it just completely separate? Like it's its own.
Miden its own completely separate. I mean, one of the
Okay.
things that we're doing with Polygon is like we will integrate with the UG layer. So UG layer is kind of will be our canonical bridge to get to Ethereum and to get the interop between other chains. But other than that, like it's completely separate from Polygon.
Okay. And so the state is basically a bunch of individual accounts that can store just an arbitrary number of bytes. Is that like a good way to think about it?
Yes. So like actually like if I had to describe an account, so there's like let's say this is a Miden account. And it consists of several things. There is a accounts have an ID. We don't have concept of addresses, but there is a concept of IDs, and I can get into it. But it's a rabbit hole that we can really get into. But like, there's an ID, there is code. So like how on Ethereum every smart contract has code. There is storage, very similar to storage in Ethereum. I mean, there's like technical differences, like it's not a single Merkle tree. You can like it's like multiple storage slots, and you can they can have different types and all that stuff. I'll skip one thing, and then there is also nonce, same as on Ethereum. The skip that I think is we call the vault. And the vault is a concept that doesn't really exist on Ethereum. I guess it exists, but in very different form. It's kind of like the balance of the account. But on Ethereum, the balance can contain only one asset, the native ETH currency. On Miden, the vault contains all the assets belonging to the account. So like this is also like really needed to solve the state contention problem, where like on Ethereum, as I mentioned earlier, like for me to transfer USDC to you, I need to update the state of USDC account, and so it doesn't quite work if I have to carry like if there's a USDC account that keeps track of ownership across everyone, like this model doesn't work. So I actually have to have all the account ownership records local in the account itself. In reality, it's just like a Merkle tree of assets. Like every asset is a 32-byte string, and you basically have a Merkle tree of assets stored in the account. And so when I decrease my balance, I can say it could be the vault could have USDC, it could have ETH or wrapped ETH or whatever. It could have Miden tokens. And a bunch like base NFTs as well. So you could have NFTs in the same vault. And so basically, like this is another nice thing is like once you have the state of the account, you have complete knowledge of the owner, like what this account currently owns. You don't need to scan the entire chain to figure out, okay, do I own some tokens in this contract? Do I own tokens in this contract? So like it fully describes the kind of the ownership, asset ownership of the account.
Yeah, so are UCC, et cetera, Miden enshrined? And if you want to launch a token, like what does that look like? If you want to launch your own asset or you're an AMM and you have like an LP token, how does that work?
Yeah, so like we have different types of accounts. There is we may like change that slightly, but there's like regular accounts that what I wrote to you, like just a regular account. And then we have a concept of faucets. And the main difference between these two is that a regular account cannot create or destroy assets. And a faucet can create or destroy assets of that it has created before. So like right now we have two different types of faucets. There is a fungible, which can issue tokens basically. So you like basically deploy a faucet account and then you specify like max supply. And again, it can have like arbitrary code that specifies how these tokens can be minted, who has the authority to do that, under what conditions, and like what schedule and all of that stuff. And then you also have the non-fungible.
And that faucet gets like a unique ID that
Yeah,
is then
exactly.
inside the vault to denote what asset it is. Okay.
Exactly. And then actually, like if you think about the asset itself, like the asset, as I mentioned, is like a 32-byte string. So part of this would be the ID of the faucet that created it, and then like you would have like if it's a token, it would have like an amount. But if it is like a non-fungible faucet, it would be like the hash of like whatever like the data that you want to put into the asset itself. So like you can imagine it being like a JPEG or a ticket, for example, an event ticket or whatever. That the hashed representation of it is actually the goes into the asset description or the asset identifier. This thing that I put here. Yeah, and so one of the things that we have on our roadmap, and maybe generalize it further to, right now we have fungible and non-fungible, but we can like generalize it where you could create like a semi-fungible as well, where you would be able to, for example, create something like a bond, which it's not only just like the ID and the amount, but it's also like the interest rate and the duration. And then you can say, okay, if you have two bonds that have the same interest rate and the same duration, you can merge them together, like or something like that. But if they have different interest rates, you would not be able to do that. So you would be able to represent this type of assets as well. It's not implemented yet. I think our plan to have it done by like September timeframe. We'll see if it takes as much time as we think.
And then so in the test net, is there a single block producer? How do you work on kind of
Yes.
the decentralization of the network? Maybe that's another topic.
Yeah, so our goal is to start as a centralized L2, and I'll explain the reason. So like, and specifically, we will be like a Validium.
And then where will all the data be posted?
So
Or
the
at
data will
least
be
the
posted in a
proofs?
separate, well, the proofs will be posted to Ethereum, right? So like
Ethereum,
through
okay.
Layer, yeah. So the proofs and the statewoods would go to Ethereum. The data, we haven't decided yet. It would need to be a different DA layer. Could be Celestia, could be Avail, could be something else. But it will go into a different DA layer. But there are several reasons to start in a centralized mode. Like one is just it's simpler. Like like we could take another year or maybe 2 years and build a fully decentralized system, but it's also like I think there is value in getting to market sooner and getting the feedback from the market and understanding like what exactly we're building. It's also much easier to evolve in a centralized way. Like decentralized networks are very, very rigid by kind of like design almost, right? So you can't change them as easily. Centralized stuff is much easier to change, and we're still like changing a lot of things. And I do foresee that over the next like 2-3 years, we will be still changing a lot. There's another thing is that safety, and this is like a tricky thing to think through. But in a system that I described, where people can execute their own transactions, if there is like a soundness issue in the proving system, if there is some kind of a bug, this bug may be fully undetectable. Like you won't even know that somebody is exploiting it, and by the time you catch the bug, it would be just too late. So the privacy preserving systems have like much harder or much bigger threshold that they need to cross in terms of like knowing for sure that like there are no bugs in the underlying system, because a bug there is just catastrophic. Like you won't even be able to do a hard fork like to recover from it, because by the time you may realize that you need to do a hard fork, it may be too late and all the funds have been drained and all of that stuff. And so launching a centralized mode gives us this ability where for the first couple of years we will run with like what we call training wheels, where we will still double check like all the proofs that are happening, and like people will send the proofs, but we will also make sure that we will do this re-execution to make sure that the proofs are actually proving the right thing.
But that requires everything to be public, right?
So you would have to be you would not have privacy against the Miden operator, but you would have privacy against everybody else on the network. So it's kind of like I describe it as a like Web 2 level of privacy, right? Like your bank knows what you're doing, but like not everybody else doesn't know what the contents of your bank account are. So you would be private against other people, but not against Miden. This gives us like a couple years, maybe even more, to like harden the proving system, catch bugs, maybe come up with a strategy of having multiple provers and things like that. And then once we feel much more confident, then that's when we can remove the training wheels and remove the kind of move to the higher level of privacy where we won't even know what's happening. But at that point in time, like I would sleep better knowing that we've battle tested the system for like a number of years before we like released it into the wild, so to say. And
And then is
so
there a plan to eventually move to not an L2?
well, so that is open as well. Like we could do this. I think there's good arguments, pros and cons. I do think it's a decision that we'll need to make in like 2 to 3 years, and so like it really depends on like what's happening at that time, right? I don't want to, especially in the blockchain world, I don't want to predict 3 years into the future what is going to happen. But I do think like Miden could be like an L1. Like there's no necessarily specific reasons why it has to be an L2. So like
What would it just conceptually look like as an L1? Would you have in, let's say, a decentralized block producer type of setup?
I
How
mean,
would
you
that
would have to,
work?
right? So, like, basically, like, the plan is to start with a centralized L2. Like, but actually, before I go there, let me finish the last point. And I think the other thing is like there's still quite a bit of uncertainty around like what is privacy and how you do it in a compliant way, so that um, in a way that like it doesn't get you in jail, or shut down or something like that, right? So while we're operating in the centralized mode, we're not subject to this issues, because like we see all the data, and so like I don't think like, North Korea will launder money through Miden because, like, again, we have the ability to like see it and prevent it if needed. And it also gives us, again, this 2-3 years to figure out the proper way. Maybe there are some safeguards that can be built in. I think it's still a subject of research of how exactly you make sure that like you make the protocol like exploitation resistant. So like, you can't allow somebody to like launder a ton of money through it, or make it like categorically, extremely difficult or whatever. But at the same time, still give real privacy to people. Like, one strawman example could be like if you're sending small amounts, let's say, 10K, like you don't need to do anything. But if you sending like like $1 billion, maybe you need to have a delay period or like some other requirements imposed on top of you, like where it makes it difficult. Like it does assume that there is some kind of like Sybil resistant identity system working, but this is like one of the approaches for like for regular people sending things should be private. But if you're sending like many millions of dollars, maybe there is like extra requirements where you need to prove that you're doing something legit. I mean, again, not saying that this is going to be the way we do it, but like this is one of the examples in which in how it could work in the future. And then so the idea is, so we start in this mode, and then over the next 2-3 years we go to fully decentralized mode. And here we'll have the decentralized, like you could have like the block production be decentralized. You can have even this individual like network transactions that I mentioned, like could be also decentralized, different searchers building them and things like that. And then, after that, like going to L1 is like really like there's not a huge difference in my mind between the decentralized L2 and a L1. There is some differences, obviously, but it is something that we can make a call on when the time comes.
So decentralized proof of thing would kind of be like almost like a proof of stake where
It could be.
it's
I mean, again,
rotating, you get to, produce these blocks at these times or something.
I think I have kind of stayed away from thinking about that like how exactly it would work, just because this is like it's a whole can of worms by itself, like solving consensus and P2P networking and how it will work. So this is like the time to market really comes from like I don't need to worry about which consensus we're going to use right now or how we're going to do P2P networking in an efficient way and all of that stuff, and then we can solve it over the next 2 or 3 years. And research will also, like, there's like new consensus algorithms come up all the time. I think we'll need to make a call on like what type of like finality we want to provide, right? Like, do we want a consensus algorithm that like can finalize in, let's say, 1 or 2 seconds, or maybe even faster? Or are we comfortable with something that takes longer? Or like, you hear like Aptos and Sui now, and even Solana like pushing below like half a second consensus, right? So all of this comes with their own trade-offs, and we can evaluate like which ones, like maybe we'll use something from Aptos, or we'll use something that Misten guys come up with. I should imagine I used to work at Facebook, so I actually work with all of those guys, and I have like I think some of the consensus stuff that is being produced by those guys is like outstanding in terms of consensus algorithms. But 2 years down the road, somebody else like Solana recently came up with a very interesting consensus algorithm, and maybe in 2 years there will be even something else. So I don't want to make a call just on that just yet.
Yeah, of course. Well, I think this is probably a good spot to stop. Do you have any kind of like concluding thoughts on Miden, like high level stuff, or like what you're really excited about going forward, just to wrap it up?
I mean, as far as Miden goes, I'm really excited. We're working hard, but I'm really excited to like having this come to fruition after like working on this for basically 3 years. It's already running in a test net, but getting it to mean that that's a whole other thing. So like super excited to get there in next 6 to 8 months, I think. And overall, I think I brought up this concept of edge blockchains. I do think like this is probably, and take this with a grain of salt because it's my biased opinion, but this is the only way to make blockchains work, really. Like both from scalability standpoint, like you just can't put the state of like if you think about billions of people using blockchains and doing it in their daily lives, like you can't have terabyte sized central state. Like there's just not gonna work. Like when you have like I guess dozens or maybe even hundreds of terabytes that somebody needs to manage. And the second one is like I don't really see how you can make blockchains work without privacy. And it's not maybe obvious now, but I do think that we're at the kind of like this cusp of where this becomes very, very obvious because of with the advent of AI, where you can train AI models on, like, let's say, blockchain data and things like that, where they can do correlation. Like, I would be able to type in your address and I will get like full history of what you did on across. It will correlate across bridging activity across every like Web 2, and now, like, just by the virtue of me having your address, I will know everything you've done in the last 10 years, and it will correlate it with your real world identity and figure out. So, like, basically, this is already possible, but this tools are available to, like, nation states and like big institutions, so to say. But you, in 2 or 3 years, I think you'll have to like chain analysis in your pocket where you will be able to do the same. The AI will break down the barriers here dramatically. And so, I mean, unless something like this exists, and maybe there are other ways to make it work, but like I don't see how people could even use blockchains like in 3 years without, because everything they do will be fully correlatable.
Because if everyone just moves a lot of their financial and other activity to blockchains, you're just saying it's so in the public and obvious for people to decipher.
Even right now, it is there. You just have to put a lot of effort into it, right? So like you can do it, but like what I'm saying is, like, with AI being able to do most of those things, you would just ask, like, there will be tools that says type in somebody's address and get their full history across multiple chains, across correlated with their real world like identity and activities off chain as well. Um, you know, you know, like current models are built on scraping the internet. They would figure out like where you've posted and what you've done. Like it's going to be really, really like dystopian if we don't figure out like a solution to this.
To privacy.
Yeah.
And it's provably private, which is also interesting. It's not just
Yep.
stored in a database or something.
Yep.
Awesome. Well, thank you, Bobbin, for your time. It was great.
Thank you for having me. Was really exciting conversation.